Okay. So welcome back. We are continue talking about this given the second part of lecture 5, which is only one theorem. So let me explain the theorem. So a connected graph G with at least 3 vertices. Let me has no cut. So I want to describe a graph with a higher connectivity. So with no cut vertex, if and only if for any two distinct vertices are connected by at least 2 vertex disjoint paths. Okay, so I want to describe a proof of such a theorem, and I will finish with a comment why I'm interested in explaining such a theorem. So what happens is that when a graph has no cut vertex, or what we call bridge, what happens? We say that the graph has connectivity is at least 2. So the vertex connectivity of the graph is greater or equal than 2. Okay.
O senhor não está apresentando para a gente ver.
Can you hear me? What?
We cannot see the presentation.
Okay. Thank you. I didn't present. So let me present my. Let me present. Present now. Window. Okay. Can you see now?
Yes.
Okay. So I'm saying that today I'm going to explain this theorem. So a connected graph G with at least 3 vertices, if it has no cut vertex, if and only if any 2 distinct vertices, you can join them by 2 paths. The 2 paths has the property that they are vertex disjoint. So it's like this. So you cannot do this. You see? You cannot use a vertex in both 2 paths. So for any VW, there exists 2 paths, P1 and P2 connecting them. I think intuitively it's very nice, because a graph has connectivity at least 2, meaning that from any point to any other point, you can find 2 different ways to go from here to there. Let me prove this theorem. One direction is pretty nice. So one direction is very easy. Pretty clear. It's very clear. So let me. This direction is very clear. Okay. So how is clear? Actually, I think you can see with this. But let me say. So for any vertex B. Let's look at the graph minus the vertex. Okay. What I want to say. So okay, for example, I got a vertex B here, and here is the graph minus vertex B. This is G minus B. Okay. So for any two vertices, say x and y. For example, here, x and y in G minus V. Because originally, by assumption, we know that there are at least two distinct paths, vertex disjoint paths, connecting x and y. And only one of them possibly contain the vertex V. So in G for any two vertices x and y in G minus V, there is at least one path connecting them. Okay, I mean in the graph G minus V. So let's say some path. Okay? Sorry, what I'm saying, this is not called a bridge. A cut edge is called a bridge, okay? So this is cut vertex. So what do you mean? What does this mean? So it means that V is not a cut vertex, okay? So there is no cut vertex. You take any vertex V and you prove that it's not a cut vertex. So this direction is pretty clear. So another direction is more difficult. Define. Let's start by. So what do we want to do? This direction. What do we want to do? We want to prove that the graph has no cut vertex, and then we want to prove that for any two vertices, they can be connected by two different paths. Okay. So first of all, we want to define a distance. The distance of x and y is the length of the shortest path which connects x and y. You see, given two vertices in any graph, it's possible. Okay, you can connect x and y, for example, in this way, and then probably you can do it in another way. So what happens is that you have different paths, and you choose the shortest one, and you call the length of this path the distance of x and y. Okay. For example, if x, y has an edge, you say that distance is 1. Okay. And if x and y is not connected by any path, in this case, you say the distance is infinity. Okay. You say that, for example, if there is no such path, then we'll say that the distance of x, y is infinity. Okay? To make the notion of distance more reasonable. So what we want to do is that we make induction on the distance dxy to show that what we want, any two vertices, distinct vertices, are connected. So this is what we want. Any two distinct vertices are connected by two paths, two vertex disjoint paths. Okay, we want to do this. Remember, this is our purpose. Okay, it's not so bad. Let me. So far, so good. The base case. So we want to induct. So what is the base case? The base case is when the distance is 1. Okay, we want to track the first situation when the distance of the two vertices x and y is 1. base case, dxy is 1. So it means that xy has a edge between them. So there is an exercise I want you to do in the list of this week. So if the exercise says the following. The graph has no, so x, either x, so the exercise says the following, exercise. The edge, so let me write uv. The edge uv is not a cut edge. So otherwise, if the edge uv is a cut edge, either u or v is a cut vertex, and the graph has no cut vertex. Okay, this is the exercise. So if the graph has no cut vertex, it has no cut edge also. So there is a relation between cut vertex and the cut edge. If you remove one edge and the graph becomes disconnected, then it means that you can think about this. Okay, so you do this exercise, and we know that this edge itself is not a cut edge. Then it means that if you remove this edge only, so you don't change any vertex set, you only remove the edge uv from the graph G, then it is connected. So in particular, there exists a path, for example, UPV. P, we use P to express the path, okay? So it is a consecutive sequence of edges and vertices. So UPV, which is a path connecting U and V in G minus UV. Okay, so what if you draw the picture, it's just something like this. This is a P, and this is UV edge. It means that there we find two paths. The first path is just one edge. The second path is P. So two paths found it. Okay, now this is a base case. Now we are considering suppose DUV is K. Okay, and we also suppose that for any pair of vertices with smaller distances, smaller than K, smaller distance admits two vertex disjoint paths. So this is our induction step. We assume that DUV is K, and if suppose we have proved that all other smaller cases, if distance is smaller than K, then we are already done. So suppose the conclusion holds for all smaller distance pairs. Okay, so since the distance between U and V is K, then we can take a path. So for example, a path. So we take a path of length K, connecting U and V. Okay. So let me do this. This is a very clever proof. We start from U, and suppose we have this path. The path has length K, and we end at the point V, and we put V prime, the last vertex, along this path except V. So what I mean is that V prime is called the predecessor of V in this path. Okay, so it's the neighbor of V in this path. And we know that in particular duv prime is k minus 1. Okay, so because the path is k minus 1, there is no way you cannot find another path which is smaller than k minus 1 from u to v prime. If you can, that means that, for example, if you find some other path which is smaller than, has length smaller than k minus 1, then this path plus v prime v will have length smaller than k minus k, smaller than k, which is a contradiction, because k is the least possible, is the shortest, is the size of the shortest path between u and v. Okay, so we know that the distance between u and v prime is k minus 1. And by induction hypothesis, there are two vertex disjoint paths connecting u and u prime. So there are, for example, P and Q. These are two paths, two vertex disjoint paths connecting u and v prime. Okay, so probably we draw this picture again with another, with which hopefully is clear. So start from u, and here I have v prime, and here I have v, and somehow I got u v prime. This is my path P, and I have u v prime. This is my path Q. Okay, so we know that G minus v prime is connected. So this is where we use the property, that the assumption that v prime is not cut vertex. There is no cut vertex. So G minus v prime is connected. So there is some path. There is, so it means that if you don't consider, imagine you remove this vertex. So there is some path. Connecting u and v away from v prime. So let me say in the graph G, in the graph G minus v prime. Okay, so let's draw that path. For example, this guy. So so it might intersect with P or Q, but it also possibly doesn't intersect any. But if it intersects one of them, it does not intersect the other. No. What I'm saying is that, so let X be the last vertex along this path, which is in P union with Q. So let me consider P union with Q, all the vertices. Let X to be the final vertex along this path, which still belongs to P union with Q. It means that from X to V, this segment, it does not intersect P, does not intersect Q. Okay? So x either belongs to P or belongs to Q. X does not equal to V prime, but x can equal to U, but it doesn't matter. So let's suppose that x belongs to Q, like what I draw here. Okay, then we can find U. Let's start from U and follow this Q. You see, follow this Q, arrive at X, and then follow this part. So let's call this part R. Let's say follow R and then arrive at V. This is the first pass, and then second pass would be UP arrive at V prime and follow to V. I think it's something like this. Am I correct? So UP V prime and then V. So the two paths has no intersection. So we finish the case for DUV equals K. Okay, so this is the second part of lecture 5. Let me finish the recording here, and we rest a bit, 10 minutes, something like that, and we come back to continue lecture 6.